Hello students, myself Jyoti Kiran, Assistant Professor, Government First Grade College, Tiptur. Today class I am going to explain eigenvalues and eigenvectors. So first we know the definition of eigenvalues and eigenvectors. We shall study certain numbers associated with a square matrix and a real symmetric matrix called the eigenvalues, and certain vectors associated with them called eigenvectors. They have variety of applications in pure and applied mathematics and engineering, etc. Next we move on to the eigenvalue and eigenvector of a square matrix. If A is any square matrix of order n and I is the unit identity matrix of the same order as that of A, the matrix A minus lambda I is called the characteristic matrix or eigen matrix of A, where lambda is a scalar. The determinant of the matrix A minus lambda I is called the characteristics polynomial and is denoted by P lambda. That is, P lambda is equal to determinant of A minus lambda I and the polynomial of the nth degree in lambda formed by setting this determinant equal to 0 is called characteristic equation or eigen equation of matrix A. The root of the characteristic equation are called characteristic roots or latent roots or eigen values of the matrix A. Let us see an example to find the eigen value of the given matrix. Let A be a matrix of order 2 cross 2. Then write down A minus lambda I characteristic matrix. Then reduce to the quadratic equation. Lambda square minus 4 lambda plus 3 is called the characteristic polynomial in lambda of degree 2. On solving this quadratic equation, we get the value of lambda is 1 and 3. Therefore, lambda is 1 and 3 are called the characteristic roots or eigen values of the matrix A. Then once again write down the characteristic equation A minus lambda I is equal to 0 on expanding this determinant for this matrix of a matrix 3 cross 3. So then we get, it is a matrix of 3 cross 3, we get eigenvalues, 3 eigenvalues, 1, 3, minus 4 are the corresponding eigenvalues for this matrix. Thus, by the fundamental theorem of algebra, we conclude that as an exactly n roots or n eigenvalues, there may be n distinct or repeated roots. Then we move on to finding the eigenvectors. Let A be a square matrix of order n if there exists a scalar lambda and a non-zero column matrix X of order n cross 1 such that Ax is equal to lambda x, then lambda is called the eigenvalue of A and x is called an eigenvector of a matrix A corresponding to an eigenvalue lambda. So let us take an example. Here the matrix A of order 3 cross 3 and the matrix X is column matrix of order 3 cross 1. Then find out the product of this matrix Ax, so which is equal to minus 1 into x. Then Ax is equal to lambda x, which is in the form of Ax is equal to lambda x, where the lambda value is minus 1 is the eigenvalue of A. Thus x is equal to minus 1, 0 is called an eigenvector of the matrix A corresponding to the eigenvalue lambda is equal to minus 1. Next we move on to the properties of eigenvalues and eigenvectors. The first property is the constant term in the characteristic polynomial of the square matrix A is equal to the determinant of A. Let us take A is equal to Aij, be a square matrix of order n and lambda 1, lambda 2, lambda n be its eigenvalues. Then write down the determinant of A minus lambda I is the characteristic polynomial. Then determinant of A minus lambda becomes minus 1 to the power of n. On expansion of this we get C naught lambda n plus C1 lambda to the power of n minus 1 plus C2 lambda to the power of n minus 2 etc plus Cn. On expanding, by putting the value lambda is equal to 0, we get determinant of A is equal to, here all the terms become, we get finally Cn. Thus, the constant term of the characteristic polynomial is equal to determinant of A. Here Cn is a constant term. Next, we move on to the second property. Show that for any square matrix A, the product of all eigenvalues of A is equal to determinant A. Let us take the matrix A is Aig, be a square matrix of order n, and lambda 1, lambda 2, lambda n be its eigenvalues. Then write down determinant of A minus lambda is a characteristic polynomial. On expanding this characteristic polynomial of degree n, it has exactly n roots. For this equation, putting lambda is equal to 0, this equation reduce it to this form. Then taken from this equation, taken minus 1 to the power of n, outside we get minus 1 to the power of n, lambda 1, lambda 2, lambda 3, lambda n. Finally, this will become positive, then determinant of A is equal to lambda 1, lambda 2, lambda n. Yes, the product of all eigenvalues of a square matrix is equal to determinant of the matrix A. Next, we move on to the properties 3. Show that 0 is an eigenvalue of a square matrix if and only if the matrix is singular. Let A be a square matrix of order n. The eigenvalue of A is given by determinant of A minus lambda I is equal to 0. If lambda is equal to 0, then determinant of A minus lambda is 0 into I is equal to 0, then determinant of A is equal to 0, therefore A is a singular. Conversely, if you take A is a singular, determinant of A is equal to 0, then A minus determinant of A minus lambda is 0, then determinant of A minus lambda of determinant of I is 0, then determinant of A is 0 minus lambda into I, then it will becomes lambda is equal to 0 because determinant of A is 0. Next, we move on to the fourth property. If A is any square matrix, then A and its transpose A dash have the same eigenvalues. Here, first let us take A is a square matrix and A dash be the transpose of a given square matrix. The characteristic equation of A is A minus lambda is equal to 0. The characteristic equation of A dash is determinant of A dash minus lambda is equal to 0. Since the interchange of rows and columns does not alter the values of the determinant, we have determinant of A is equal to determinant of A dash, then we equate these two, then we get, since I dash is equal to I only, A minus lambda I O dash, then it will become, apply this property A plus B O dash is A dash plus B dash, then we get determinant of A minus lambda I, therefore determinant of A dash minus lambda I becomes determinant of A minus lambda I. This implies the characteristic equation of A and A dash will be same. Hence, the matrix A and its transpose A dash will have the same eigenvalues. So, next is the property 5. Every eigenvector of a square matrix corresponds to one and only one eigenvalue of A. Let us take two eigenvalues, lambda 1 and lambda 2 are two distinct eigenvalues corresponding to the eigenvector x of a matrix A. Then we can write it as Ax is equal to lambda 1x and Ax is equal to lambda 2x. Therefore, these are all equal. Ax is equal to lambda 1x is equal to lambda 2x. Then this equation reduces to lambda 1x minus lambda 2x is equal to 0 because LHS is Ax. Then lambda 1 minus lambda 2 x is equal to 0 but x is not equal to 0. This equation becomes lambda 1 minus lambda 2 is 0. This implies lambda 1 is equal to lambda 2. Hence, every eigenvector corresponds to a unique eigenvalue. Then property number 6. Here show that every root of the characteristic equation is a characteristic root of the square matrix, or the equation Ax is equal to lambda x as Non-trivial solution X if and only if lambda is an eigenvalue of A, or for a square matrix A, lambda is an eigenvalue if and only if there exists a non-zero vector X such that Ax is equal to lambda X. Let us check. In the proof contains lambda be the eigenvalue and X be the corresponding eigenvector of a matrix, square matrix A. Then this can be written as A minus lambda is equal to 0. Here A minus lambda is a singular. Hence, if A minus lambda is singular, then lambda is a eigenvalue of the given matrix A. Conversely, if determinant of A minus lambda is 0, then for non-zero eigenvector X, we have A minus lambda X is equal to 0, Ax is equal to lambda X, because identity into X is X only. This shows that every root of the characteristic equation is a characteristic root of the given matrix. Next we move on to the seventh property. Here, if X is an eigenvector of a matrix A corresponding to the eigenvalue lambda, then for any scalar k is not equal to 0, kx is also an eigenvector of A corresponding to the same eigenvalue lambda. Here in the proof contains X be a eigenvector of a square matrix A corresponding to the eigenvalue lambda, and this X is not equal to 0 and Ax is equal to lambda X. If k is not equal to 0 with any scalar, then kx also not equal to 0. Then A into kx is equal to k into Ax. So this can be written as A into kx is equal to k. From equation 1, Ax is equal to lambda x. Then this implies A into kx is equal to lambda into kx. Therefore, kx is an eigenvector of a square matrix A corresponding to the same eigenvalue lambda. For different values of k, there exist infinitely many eigenvectors corresponding to a single eigenvalue. If lambda is in the next property, if lambda is an eigenvalue of a square matrix A, then for any scalar k is not equal to 0, k lambda is an eigenvalue of the matrix Ka. In the proof part contains, let X be an eigenvector of a square matrix A corresponding to the eigenvalue lambda. Then we have X is not equal to 0 and Ax is equal to lambda X. Here k is a scalar, k is not equal to 0, then kx also not equal to 0, then it will become k Ax is equal to k, Ax is lambda x, then this can be written as Ka of x is equal to k lambda of x. Therefore, k lambda is the eigenvalue of the matrix Ka corresponding to the eigenvectors x. Next we move on to the property 9. If x1 and x2 are two eigenvectors corresponding to the eigenvalue lambda of a square matrix A, then this can be written as alpha x1 plus beta x2, where alpha is not equal to 0 and beta is not equal to 0 are scalars, is also an eigenvector of A corresponding to the same eigenvalue lambda. In the proof contains, suppose x1 and x2 are two eigenvectors corresponding to the eigenvalue lambda of a matrix A, and alpha and beta are two non-zero scalars, then we have ax1 is equal to lambda x1 and ax2 is equal to lambda x2. Then the above equation can be written as A alpha x1 is equal to lambda alpha x1 and A beta x2 is equal to lambda beta x2. Adding these two equations, we get A LHS we can add, and RHS we can add, and taking A is a common, then it will become alpha x1 plus beta x2 is equal to, here also take lambda is a, in the RHS side take lambda is a common term, lambda of alpha x1 plus beta x2. Therefore, alpha x1 plus beta x2 is an eigenvector corresponding to the same eigenvalue lambda. Similarly, by taking alpha is equal to beta is equal to 1 in equation 1 and 2, we can prove that x1 plus x2 is also an eigenvector corresponding to the same eigenvalue lambda. So in equation 1 and 2 we have to take alpha and beta is equal to 1, then it will become x1 plus x2 is also a eigenvector. So next we move on to the property 10. If lambda is an eigenvalue of a square matrix A, then lambda square is an eigenvalue of A square. If lambda is the eigenvalue of a square matrix A, then there exists a non-zero eigenvector x such that Ax is equal to lambda x. So we have the result Ax is equal to lambda x, A into Ax is equal to lambda into Ax. Then it will become A square x is equal to lambda into, again Ax is lambda x, A square x is equal to lambda square x. Therefore, lambda square is an eigen value of A square. So next we move on to the 11th property. If lambda is an eigen value of a non-singular matrix, then 1 by lambda is an eigen value of A inverse. Second one is 1 by lambda determinant A is a eigenvalue of adjoint A. Let x be the eigenvector of a square matrix A corresponding to the eigenvalue lambda. Then we have Ax is equal to lambda x. So take Ax is equal to lambda x. For this equation, pre-multiplying both sides by A inverse. So we get this equation. Here A is a non-singular. Then operate A inverse of A becomes I. Then it will becomes x is equal to lambda A inverse of x. Then find out A inverse of x is 1 by lambda x. Therefore, 1 by lambda is an eigenvalue of A inverse and x is a corresponding eigenvector. So next in second one, take Ax is equal to lambda x. For this equation, post multiplying A inverse on both sides, we get x is equal to lambda A inverse of x. Then multiply by lambda divided by lambda, 1 by lambda x is equal to 1 by determinant of A adjoint of A into x. But here A inverse is 1 by determinant of A into adjoint of A. Then 1 by lambda determinant of A x is equal to adjoint A x. Therefore 1 by lambda determinant of A is a eigen value of the matrix adjoint A. Thank you.